talk is based on this book, The Sun in the Church, Cathedrals as Solar Observatories by J.L. Heilbronn. This book first came out in 1999, the hardcover, and it was well received. The report from that appeared in Sky and Telescope was excellent. And then apparently a paperback came out 2 years later. It describes the problem of determining the calendar and a type of a very unusual type of astronomical instrument called the Meridiana. And I had personally never heard of this kind of instrument prior to reading this book. And Ken told me he had trouble finding it on the internet, which is even better. The cover shows a photograph of St. Peter's Basilica in Vatican City. Now, this is a basilica, it's not a cathedral. Okay, fine. But there are no Meridiana in St. Peter's. There is one elsewhere in Vatican City, but not in St. Peter's. This is just a pretty picture. And it must have been done after some sort of liturgy where incense was used. So that's why you have those beams of sunlight coming through. But in any case, most Meridiana were constructed for the purpose of determining local time. And as a matter of fact, they were used, the last that I know of being used were in Belgium in the 1830s for the purpose of railroads. It was extremely important to know what time it was if you're using a single track railroad. And more than one, otherwise we have a Casey Jones situation. Some were used to determine the calendar as well, and some were used for other scientific purposes. Now, getting to the calendar problem, this is something that we're all familiar with. The year is not exactly 365.25 days long. If it was, we could just have a leap year every 4 years, and that would take care of everything. How do you have an accurate calendar? Traditionally, two systems were used. One was to regularly calibrate the calendar. Most ancient calendars were not 365 days. You know, the Islamic calendar would have 12 months of 28 days. The Hindu calendar had 12 months of about 29 or 30 days. Mayan had 18 months of 20 days. And then what these various societies would do is they would find a way of introducing a makeup month in one manner or another. And then that would in turn recalibrate the calendar so that the spring equinox occurred when the calendar said so. And that actually works very well if you're dealing with a city-state. As nations became larger and as we started having an empire, how do you coordinate all of this? Well, the other way is to have it, plan B is to have an extremely accurate calendar, but that's very hard to do. Now, the Romans found this out the hard way. That, by the way, that statue, that famous statue of Julius Caesar was made after he died. And if you really want to know, he did not look like Richard Burton. He looked more like a bald version of Gomer Pyle or Tiny Tim or something like that. If you don't know, recent research has shown that he was homely with a big nose and bald. But nevertheless, Caesar came up with the calendar in 45 BC. What had happened was when he knew there was a problem, the Romans originally picked up the Etruscan calendar, which was, of course, in the earlier civilization in central Italy. And what the Romans did, they had a calendar of 355 days. And then every few years, they would enter another month. They called it the mensis intercalaris, which is the intercalary month. What was unique with the Romans was that they didn't introduce a 13th month. They introduced a month into February. It would be after roughly February 23rd. There would be another 22 or 23 days. Then would come February 24, 25. So after February 28th was always March 1st. Now, it may sound crazy. This is how they did it. And I don't know exactly why. And it's not necessarily germane to this. But when in 48 BC, when Caesar went to Egypt for other reasons, he did find out, he met with a Curius who explained that previously the Persians had a leap year. They developed that around 503 BC. Egypt picked it up at around 238 BC. Caesar becomes aware of this and says, hey, this is an improved calendar, goes back to Rome. He meets in 46 BC, was only 2 years before he died, by the way, with Sosigenes of Alexandria. And it was a great idea, wonderful idea. And Caesar gave us first of all, he made 44 BC 445 days long to recalibrate the spring equinox. They were having so many problems, they didn't get around to introducing the meses intercalaris. And he gave us the bisextile. Now, bisextile sounds like a subject that you're not supposed to teach in public schools in Florida. Or
Florida's getting no love today.
yeah, or it might sound like something that happened in somebody's college dorm. I don't know. But in any case, what it was, after the Sunday is the first day of the week, Saturday is the seventh day of the week, Friday is the sixth or the sextile day. So they would introduce every 4 years a bisextile. Now, this may sound crazy, but what it means is every 4 years, one Friday in February existed for 2 full days. That's all. And we still have, after February 28th would come March 1st. It may sound crazy, but this is how it was done. Later on, slowly, the bisextile was added with February 9th, 29th being the leap year, and it slowly evolved in others around Europe. And actually, the last nation to get rid of that was England in 1750 with the Calendar Act. They were still using the bisextile. Now we have leap days. And I remember in high school once somebody telling me that it was February 29th. That was when he was born. So he was at that point 4 years old. And I said, tell that to the draft board. Okay, it wasn't going to work. But in any case, that is the Julian calendar. And as you know, the year is not exactly 365.25 days. And on average, this would have an error of 11 minutes a year. It was good enough for government work. They knew about this at the time that this was, at least within a couple of years after Caesar's death, they realized that this was off. It wasn't enough to cause a problem. Now let's introduce the problem. And that's Easter. Now remember that the Christian calendar, as like many other calendars, is not just solar, it's also lunar. That complicates things a lot. How do you calculate Easter? Well, if you don't know, Easter is the first Sunday after the first full moon after the spring equinox. Sounds simple, except sometimes maybe the full moon occurs at 11:59 p.m., right after the equinox, or the first Sunday might be at, or something like that, where these things are, you got to know these moments to within minutes or seconds. Another problem comes with human nature. At this time, there was no postal service. Most of Europe didn't even have roads, which meant every pastor of every church had to calculate Easter himself. And they did not have formal education. In fact, this was one of the major complaints that Martin Luther had, and in response came the Council of Trent, and one of the reforms was to create a seminary system which requires training. Priests were not trained. They used the system of a trade, like a tradesman. where you would be with a master and you would become a journeyman and all. Well, they did that something similar with the clergy. So the boy would be an altar boy and then become an acolyte and finally become a priest. Now, the problem is that there's no central training. People can be very emotional and rigid. I'm sure this doesn't surprise you. And God forbid that town over there, there's somebody calculated Easter wrong. They would guarantee someone would flip out. Now, this is not unique to Christianity. I've seen extremely doctrinaire and rigid people in the Jewish faith, in Muslim, Buddhists, and you don't have to be religious. I've seen very doctrinaire and rigid people who are atheists. This is human nature. Many, and I'm emphasizing this because many people who you might be religious and say, okay, so the guy next town came up with the wrong date. We'll go over, explain to him how to do it, and then everything will be fine. But please appreciate that not everybody's like this. That's the only point I want to make. I'm not criticizing anyone. However, they knew this had to be solved. There are two solutions. The minority opinion was simply have a set date for Easter. I mean, we have Thanksgiving is the third Thursday in November. Okay, it's not worldwide, but nevertheless. Why not have Easter being the second Sunday in May? Not have to worry about it. Now, all you have to do is get a very accurate calendar. Or you can have a very accurate calendar, but it also has to make sure that the lunar calendar works with it also. This is not easy. And it took centuries. It took really 1,000 years. And so this problem continued. Early forms, back in the 500s, Pope John I asked Dionysius Exiguus for his advice on the problem. Dionysius means Dennis. Exiguus means the lowly. He was a monk. He was a mathematician. He was a compiler of canon law, but in other words, this is Dennis the lowly, Dennis the monk. Okay, if you really want to know what it translates to be. Now, previously, there was 200 years before them, was the Emperor Diocletian. Diocletian standardized, he reformed the monetary system, he reformed the government, he reformed taxation. He was one of those guys, he comes in, he tries to reform everything. Many dictators do that. He also decided he was the one who tried to eliminate Christianity. Beforehand, the troubles that the Christians had was really a riot here, a problem in that province. There was really no central, but he tried to do away with it completely. He was never forgiven for that. Dionysius did two. Now, Diocletian centralized that every time that there's a new emperor, the whole of the empire starts with year 1. Previously, although they were using the bisextile, every province had its own year 1, depending upon who the governor was. Now remember, they didn't have a year 0. The Japanese were doing the same. Their calendar started with year 0, which was the first year of the emperor. And when Hirohito was emperor, first became emperor, there was an aircraft designed, and it was named after that year. That's why we were fighting the 0. It was developed the first year Hirohito's. But, okay, Dionysius, it started with year 1. And then, Diocletian. And good old Dennis came along and decided we'll recalibrate. So year 1 would be the birth of Jesus. Yes, he was off by a couple of years, but that's why we have AD and BC. Or BCE now. That's where all that comes from. He proposed dropping the leap year every 134 days, not the most accurate way of handling it. But 134 is the golden number. It's the number of years when the lunar cycle goes back to the same position. He's trying to calibrate both. And he calibrated Easter for quite a long time. His first reform became the law. The second two were not. One of the reasons was they realized that the leap year, that was not accurate enough. Goes back into committee for another 1,000 years. Till this gentleman, now I have two versions of his last name, so I don't know which one was used in his time. But Luigi Giglio in 1575 proposed corrections to the calendar, and these were, he created what is now the calendar that we have. They were accepted in 1582 by Pope Gregory XIII, and that's where we get the Gregorian calendar with the leap, with very few minor improvements. That's the calendar we have now. However, this was 1,000 years too late, because if 1,000 years earlier this had been adopted, it would have gone across Europe no problem. By this time, the only thing Pope Gregory could do was improve the calendar for the Papal States, which was in northern and central Italy. It took centuries for the rest of Europe to adopt the Gregorian calendar. In the 1700s was when England had the Calendar Act. Some countries didn't adopted it in the 1920s. If you know the history of World War I, there was a problem when the Western Europeans and Russia said we were going to have an offensive. At the same time, they were both using their own calendar, and it was off. The Ukrainian Orthodox Church adopted the Gregorian calendar in last June. So this past December was the first time they celebrated Christmas on December 25th. And it still goes on. Now, that's the calendar issue. And I wanted to just do that briefly. It's a major part of this book. It goes into a lot of detail. Let's talk about now some churches. Santa Maria Novella, which means New St. Mary's. This church was on the site of a previous chapel. And Ignazio Danti designed a quadrant and amaryllis field for the church. And you will, I don't know, let me just put this, oops, go back. I want a pointer. Here's just above the point is the quadrant. Now the amaryllis field is just above here. You can't see it here too well. This particular church happens to face roughly north-south. So there was a good place to put these instruments. Dante, remember this is Dante with an I. He's the mathematician and the map maker. Not Dante with the E, who's the guy who wrote the Inferno, okay? You see him pictured on the right. If you don't recognize, he's wearing a Dominican habit. The Dominicans were a teaching order. Santa Maria Novella was a Dominican church. For them to have a scientific instrument is an extension of their mission. And so this was not difficult to do. The church was already 250 to 300 years old, depending upon if you want to count when it was finished or started, which meant it had already settled, which meant any movement of the building had already finished. Nice idea. Here's the instruments. Now, the quadrant, you can see 1, 2, 3, 4, 5, 6 gnomon on it. There's 6 charts on it. It was a nice idea. Here's the amaryllis sphere. You see the 2 circles. The circle that's almost facing us, the one in the middle, that would be able to read 12 noon. Now, many people would think that what you're doing is you're having the shadow of the front and the back projected onto the building. That's not true. What's happening is, now remember, the sun is not a point of light. The sun is an extended object, a half a degree. So all shadows of the sun have a shading on either side. They're not sharp. So you would wait till 12 noon, look at the shadow of the front ring against the back. And when it's balanced on both sides, if the shading is equal, that's what 12 noon is. This is not an easy instrument to use. The other ring would do the same thing with spring and autumn equinox. Equinox? Right. One problem, these instruments were not put up accurately enough. In addition, they're way too high. The only way a person could actually use it would be to build a platform and go up there. But this problem of not having things accurately put, unfortunately, would be a problem that Dante had his entire life. Not easy to do. But he came along and came up with another instrument called the Meridiana. Now, the Meridiana involves putting a hole in a wall. This was to the right of the rose window. And it was 21 1/3 meters up from the ground. Now, that hole is called a gnomon. It's the same as the pointer on a sundial. Think of it as a sundial on steroids, because this could be used to a size that is impractical for a sundial. Yes, you can see you can use a sundial, but this would be far more accurate. If you look at the drawing on the right, the line that goes from H to A, that would be summer solstice. H to B would be winter solstice. H to C, spring and fall equinox. So what you do, draw a line down the floor of the church, and you can measure the movement of the sun extremely accurately. Here it is from the inside. You see the summer solstice marked by that medallion on the bottom, and you see the line coming up. Notice it doesn't quite line up with the tiles of the church. The church is not exactly north-south. One good thing for Dante, as I point out, this church is aligned north-south. The preferred position of a church would be to align it east-west, with the people coming in the west side, facing east, facing the sunrise. That is the preferred position for a Catholic church, or at this point, it was a Christian church. It was at this time. By the way, this image was done in the morning, which is why the sunlight is on the floor, going through a stained glass window. The actual gnomon was sealed up a long time ago, simply because having a hole in your wall means rainwater comes in. It's not always the most wonderful thing. Now, this was not the reason for using a church. One of the reasons is the bigger, the more accurate. The bigger, the better. Meridiana were put in other kinds of places like city halls and things like that, but usually churches were the largest open spaces that could be found. That was the reason. The largest was actually constructed about a century earlier. Santa Maria de Fiore in Florence. Now, this church is massive. In fact, it's so high that the gnomon is so high that you could take the next four largest, stack them on top of one another, and they don't get to the height of this. The absolutely massive church. I will point out that around the asp of the church, there are four major chapels and a couple of smaller ones. Each chapel had four buttresses, and they had hired 12 artists to put statues on top of that. One of them was Michelangelo. That was the David. There's a fiberglass copy of the David where it was supposed to be. They did that in 2010 just to make it look pretty. It has nothing to do with this talk, but people know about the statue. Now, why he had such detail, like the veins on the back of his hand, when nobody would see it from up there, I don't know. But nevertheless, this is the diagram of the inside of the church. The gnomon is up in the lantern, which is that thing on top of the dome. So during winter solstice, the sunlight would not even leave the lantern. during spring and fall equinox, the ray of sun would come down only into the dome. It's only during summer solstice that this ray of light would reach the floor. It's not completely understood why this was constructed because the drawings have been lost. But it was used to check the inclination of Earth's axis and how it changed over time. Something this size could do it. And from the inside, you could see here, that shelf on the left was added in 1510. It's 2 inches in diameter, and that is 5 centimeters. Let's go with the metric system. And it was 90 meters above the floor. You're looking up on the right into the dome, obviously highly decorated, and the light area in the section is the lantern, which is why it's called that. It's a way of bringing light into the church. Now, the image on that circle would be the size of the sun's image at summer solstice. You see how big it is.
Wow. Which circle? There's the small circle.
I don't know the purpose of the small circle. The large circle is the image of the sun. There are sometimes details that are not being recorded even when you go to these sites, because a church like this has a website and a lot of description of this, but it's written for tourists. You know, it's not written for scientists. And some of this stuff, you have to appreciate the limitations of the ability to do research. However, the gnomon is opened up in the spring for summer solstice. It was in use until the mid-1700s. And you see on the left, that small picture, how the sunlight will appear earlier in the day. And you see now, here is that image of the circle with the circle in it. Here's the sunlight. You can see that it is the same size. Notice the brass line. It doesn't perfectly align with the pattern on the floor because this was added on. This is now, like I say, it's used for demonstration purposes. So if you are ever thinking of going to Florence, you may want to consider doing that in June because you'll be able to see this. So far, so good? Okay, now let's move on to San Petronio, Bologna. Now this church, which this is a more complicated situation, and this I know some of the details of. This is the largest Gothic brick church in the world. There's another one of those massive churches. Bologna is home to the University of Bologna, which is one of the oldest universities in the world. Some claim it is, let's not get past that whole controversy. Copernicus studied here. He studied canon law. And to have a scientific instrument here is consistent with this city being a center of learning. Also understand that it would also be consistent with it being a church, because when you're studying science, you're studying God's creation and how it works. This business of science versus religion is really a 19th and 20th century fight, and it mostly involves evangelicals. Okay, it is not something that we see here. This also was not church property. It was owned by the city of Bologna. And it was the city council that got together and financed the construction of the Meridiana. This was not transferred, although Mass was said here and religious services. By the way, if you look down here, this is all kinds of fancy shops and stuff like that. So think of Woodbury Commons in Italy. That's really what's all around here. The university is off on this side over here. Okay. The ownership of the church was never transferred to the Catholic Church until 1921 as part of the Lateran treaties. But until the idea that you would have a secular organization owning a church better not surprise you, because the largest number of churches in this country are owned by the General Services Administration of the federal government. in case you don't know it. Why? Look at military bases. They have chapels in them. And if you go to a diocese, many of the churches are owned by religious orders, or especially these older parts of the US, they may be owned by a board of trustees. And the diocese provides priests, but they do not own it. This is part of the complications of how life is. In any case, they had one time, what you see was constructed between 1390 and 1479. In 2017, a contract was awarded to finish the marble facade. Dante, our good friend, came in. We are slightly west of due north. This is roughly north-south, but less as accurately as Santa Maria. So, but we're on the north side of it, so you notice the sunlight, we're in the afternoon, and thus the north side does not have the sun. Dante created a meridian, and it was off by several degrees and was useless. Enter stage left, a good friend of ours, Giovanni Cassini. And he decided to make another meridian. Now, later on, he became the director of the Paris Observatory. So in that painting, that's what's in the background, along with a telescope. It looks like a tower crane or something like that, but that's actually a telescope. Remember, refractors then had to have extremely long focal ratios, and that was one of his major achievements. Giovanni Cassini figured out how to put a very large and very accurate meridian there, because in order to do it, you now had to deal with the fact that there were columns in the church. This is so large, this particular church. This church is so large that if you could do away with the columns, you could play a football game there. Okay, not quite as impressive as the original convention hall in Atlantic City, where they did have football games, but you get an idea of the size of some of this building. So what he did, he put the gnomon about there. Then he lined it perfectly so that the meridian line threads between the columns. And it's just high enough that it reaches the back wall without touching it. This is from his book. He printed this book in 1695, and you can download it. The meridian line itself is 219 feet long. You can see how massive this building is. And you can see it's not quite to scale, but you see the different lines and the different signs of the zodiac showing the places where the sun would land. Now, he also did another thing. In order to make sure that the central line was accurate, now forgive the curves, I don't know why you were introduced into this. Imagine, think of a rain gutter. He put a trough next to it. They already figured out how it could be straight, but they had to make sure it was, they filled this with water, so that with this device, you could transfer the height of the water to the line and make sure the line was at a perfect height. Now, you would be forgiven if you thought that this was to make the line perfectly level. It wasn't. It was to follow the curvature of the earth. At 219 feet long, the curvature of the earth becomes an issue. Understand, this is before calculus. This is before the development of the slide rule. Everything had to be done by hand. Everything had to be calculated. And anything that could be done to simplify things was incredibly important. So there's a whole level of calculations could be removed if you follow the curvature of the earth. And here's what it looks like on the inside. What you're seeing is the meridian line. Again, it goes across and threads between the columns. You don't care that 5 minutes before and 10 minutes after it's touching a column, as long as at 12 noon it's on that line. You'll see here is a wider disc explaining what sign of the zodiac it's in. Here you see a sign that describes what's going on. The light in the background is an ornate cross, because that is the altar area. Here's another photograph. Again, you see how it threads between the columns, and you see these plaques. This is one half of one plaque. It's for February 15, 16, 17, because you get the idea when the dates are. Here's the symbol for Pisces. Here's one of the Pisces fish. The other one's hard to see because of the grain of the marble, but you get the, don't be surprised about seeing the signs of the zodiac. First of all, they weren't antagonistic towards zodiac astrology, unfortunately. But besides that, this was simply a symbol telling you what's going on. This was in Pisces. At some point, it was in Sagittarius. Again, we do this all the time, and we don't feel we're being astrologers. It's the same thing here. It's for science. Now what just happened here? Okay. Here is on the left is the gnomon. It's made pretty because they decorate everything those days. Cassini also calculated that the hole, now if you make the hole too big, the image is fuzzy. It gets sharper and sharper as the hole becomes smaller to a point. Beyond that point, you get diffraction effects. Cassini calculated that the gnomon hole, the best size would be 1/2 of 1% of the elevation. So if the elevation was 100 feet, you want a 6-inch hole. Now here we're looking at on the right an image of the winter solstice. So the image is large and elongated. And you see how this may be like a day from winter solstice. So the image is not quite perfectly fitting it, but you get the idea. Difference between summer solstice and winter solstice. Summer solstice, you're talking about roughly a 10-inch diameter. Winter solstice is basically 25 inches by 66. Those are the sizes. Now, the next church I want to point out is Santa Maria degli Angeli e dei Saint Mary, the most blessed Virgin of all the angels and martyrs. Remember Diocletian, the guy who tried to eliminate Christianity? They decided to put a meridian in a building that he constructed, getting even with him. Okay. This is located about 4 blocks north or 2 blocks north of the central train station in Rome. So if you happen to be going into Rome by train, or if you happen to be near the train station, just north of it, from the outside, it looks like hell. The reason was, here again, this was not church property, but this building was always maintained. This is a massive complex. This goes on for acres. These are massive baths, but it was sold to the people of Rome as, by building this, the church will stay. The building will be kept. Remember, look at the Colosseum. People took the marble off to build their own buildings. The Colosseum never collapsed. It was taken apart. Not just the marble, but the other stones also. The same thing happened with the Great Pyramid at Giza. It was covered with marble. People said, I want that, and took it. They just left it on the top, the little capstone there. And the Baths of Dionysian now have this basilica, and there's an art library, there's a museum rather, there's an art school, there's several things there. 1911, the people of Rome got together and said, we want this removed. So you see, much of the facade was removed and the original bricks were exposed. The baths would have had The church is on, remember, there would have been a cold bath, a frigidarium, and that's where the church is. There would have been a lukewarm bath and a hot bath, the caldarium. Those were not used. This is still a massive church in one, and plus they had a large library and other things. But this is a huge complex. This is the inside. On the left is a rendering of the inside from ancient times, and on the right is what it is today. Remember, this is not a few hundred years old. This goes back to classical times. Okay, the floor may have been replaced, I don't know. But everything else you're seeing, most of what you're seeing here, it goes back to Diocletian. And here is the meridian line. Now, I'll get to the circles in a little bit, but if you look on the image on the left, here you see the line. I'm going to try to point here. And this is for, I'll get to this, but the meridian was built in 1702, fairly late. Now, it was necessary to put a gnomon in, so that was literally cut into that arch, quite crudely. There was no attempt made to make it look pretty. Okay, it's just a groove in an arch with a papal symbol above it, but nevertheless, there is that, obviously a photoshopped beam of light, but that's okay. That's what it looks like. And on the ground, these instruments were real works of art, by the way. They're massive. And you see how the light would come down, and it tells you what's going on where. Now you notice the stars are even then mentioned. We'll get to that in a minute.
The dark line, is that a darker marble or is that brass?
Brass.
Wow.
All of them, I believe, use brass. It's more malleable. And in fact, on the right, you can see, by the way, the question was, what's the dark line? You see that you can see the polish of the brass there, the old brass. It looks like the numbers are filled in with brass also, because you see on the right how 36 is shining.
Yeah, wow.
Okay.
It's spectacular that it's laid into marble all by itself, as opposed to the other one where it's just the brass and the regular floor.
Yeah. Now, here's it being used. The arrows point to 3 pieces of white paper. And the middle one would come in contact with the sunlight first. That would be first contact with the meridian line. So here's obviously a live demonstration. See some of the beautiful artwork at the bottom of this, by the way. And then the other 2 lines represent the midline. That would represent 12 noon. That would be when the sun reaches the meridian. Now, something else was done here, which is unique to this, which is a second gnomon was put in. The solar gnomon is on the right, and a second one was put in to observe the North Star. That's why the circles. To observe the movement, the changes in the position of Polaris. Not just during the course of the year, because it makes a small circle, but also see how the Earth's axis is changing with time. Now, a star is not going to show a shadow, but you could do so if you put a telescope there. So what you see represented on the left, upper left, is the south gnomon with the sunlight coming through, and on the right is the north gnomon, the light coming through, and in front of the telescope you see the circle, which is really where this the starlight would be going. They also used the same telescope on the south gnomon to observe bright stars. Now, this would only work if you have an extremely dark church. Well, churches are fairly dark. You just turn off all the lights, well, snuff all the candles in this day, and it would work. And that this was done for a lot of scientific purposes. before we go any, and we'll get into what the science was, but just the next part of our trip is to Saint-Sulpice in Paris. This is the second largest church in Paris after Notre Dame, and it's the largest one that's open right now because Notre Dame is being repaired. Now, 1727, a lot of opposition to Galileo was being relaxed, and here was another chance to set the story straight in terms of science. You see on the bottom, here is your meridian line going up, and it actually goes up that obelisk. And the marker on the bottom there, by the way, the Meridiana was designed by Henry Sully, who was an English clockmaker. It was built for Charles Claude de Monnier to determine the date of the spring equinox, in other words, the date of Easter. So it's for calendar purposes. On the bottom, for the nuation of Earth's axis and obligatory of the ecliptic. That's the Latin on the bottom of that stone. The sunlight comes in from that hole on the top. If you look up this church on Wikipedia, it will point out a second hole down here. I don't know if that's an error in Wikipedia or if there was a second gnomon, in which case I don't know what that gnomon would have been doing. But I don't know if the Wikipedia article is correct. This does explain that there was the gnomon, 25 meters high, which is 82 feet, and it goes along the floor and up that obelisk, which was meant to point out the light in wintertime. Dan Brown puts this in his book, The Da Vinci Code, and says there was an Egyptian temple on this site or something like that, which is complete fallacy. Look, it's a wonderful book. It's very entertaining, but it's false. As long as you take it as fiction, everything's fine. Last, the Tower of the Winds in Vatican. Traditionally, if you're going to show the Vatican City, it's pretty to put east down here, west up here, because that aligns St. Peter's very well. South, north. Look at just above my pointer, there are two modern skylights. Tower of the Winds is up there just above it. Turn it around. Now, north is on the right, and west is on the bottom, and the Tower of the Winds is now, you can see that it is a tower above those modern skylights. This was put in by our good friend Dante, but only as a demonstration. The image is photoshopped. The light doesn't show like this. Interesting, it's cut into the painting of the calming of the Sea of Galilee, which you see in the calming of the storm. But in any case, now, trying to observe with these things is very, very difficult. This is a very difficult instrument to use. One of the problems is obviously clouds. We've seen them recently, right? Seeing, because if the air is turbulent, the image is going to bounce all over the place. And I mentioned that the images, the sun's edges are not sharp. So what they're trying to do as the sun gets to the meridian line is look on this side, and which is, when is it balanced? Very, very hard to do. Cassini said that he could, when the seeing was good, he could measure the sun to within better than a minute. And if it was exceptional seeing, he could do it a lot better than that. Modern people have used these instruments. They've studied this and said this is really quite an accomplishment. However, Cassini was noted for being an exceptional observer. They said it's physically possible. He was probably not exaggerating. Another problem is the times for the equinoxes and solstices, they are not exactly at 12 noon. So this year, solstice may have been at 4 in the morning. Well, you're only measuring 12 noon accurately. The way that gets done is to measure all of this year after year after year, compile all this information. Hopefully it was all done accurately. And with that, you get a more and more accurate measurement. In other words, you're improving the signal-to-noise ratio. With that, you can get extremely fine measurements. But there's another problem also that has to be calculated. And believe me, these people need to calculate everything. Analemma. 12 noon only corresponds with the two equinoxes and the two solstices. At other times of the year, 12 noon is not at the meridian time. It's not when the sun is directly overhead along the meridian. By the way, Dennis, this was known, first described in 570 BC by Anaximandros, who was the student of Thales, by the way. It was probably known earlier. But all of these calculations had to be done very, very complicated. The photograph of just having a camera look at everything at the same time, if it was oriented at 12 noon, it would be straight up and down. But this was done picturesque at an angle like this. The first person to actually photograph the analemma was Dennis Sisico, who printed it in Sky and Telescope a number of years ago, and then other people have done it. I just like this picture because of it's pretty. But Dennis Sisico is actually the first person who created this image where he photographed this effect.
He bolted a 4x5 to his windowsill in his house in Massachusetts. And, Dennis Sisico bolted a 4x5 camera to his windowsill. He used one piece of film for the whole year. I mean, you have to imagine that he doesn't forget anything, because one mistake takes the dark slide out at the anointed time, takes one picture, puts the dark slide back in, and then doesn't touch the camera until it's time for the next exposure. It's an astounding project.
As we all know, astronomy, to really enjoy it, takes a certain amount of insanity. Okay. Other issues, by the way, data reduction. I already said it's very, very difficult, and very easy to make mistakes. What astronomers were doing at this time, we already are at the point where Kepler had come along with his law that as objects get closer together, their velocity in the orbit increases, and then it decreases as they get further apart. So as the Earth got closer to the sun, its velocity in the orbit would increase, and then it would decrease as it went towards further away. A planet with more elongated orbit like Mars, you would see this more extreme. With a more circular orbit like Venus, it would be more regular. The data reduction just became that much more difficult, because you have multiple variables. Kepler said equal area for equal time. So the further away, to have equal area, you have a narrower angle. But as you get closer, the angle will open up. You wind up with equal area. Okay. What some people did was to use Tycho Brahe's cosmology, which said the Earth was at the center, the planets were circling around the sun, which circle around the Earth, because the math was easy and it was good enough. Other people were saying, no, you got to do the thing with the sun in the center and do the Kepler's math, but this was a horror. Ultimately, to solve that problem, Isaac Newton developed differential calculus, which can handle multiple variables at once. That was the reason for it. Okay. What were the results? Now, first of all, let me explain something about how astronomy works. We think of the great discovery. You know, Galileo pointed a telescope at Jupiter and he saw moons. No one in any way thought there were going to be moons around Jupiter, but they observed it. You could see that by the patterns that they were clearly going around Jupiter. Or you see in our day, the Hubble telescope with the deep field image. They took this deep field picture of an area that was supposed to be empty, and they looked at it, and maybe there would be a couple of galaxies there. It was chock full of galaxies. Nobody expected this, or at least very few. That's not how science normally happens. What happens is somebody observes something, and then we start measuring it closer and making better and better measurements. The Meridiana never discovered anything new or different. But what they did was a massive improvement in measurements that brought astronomy forward by leaps and bounds. What did they study? They studied the length of the year, local noon, and I'll get into this in the local. Now, length of the year, local noon, you could understand. Local latitude, of course, because if you were measuring the angle of the sun that accurately, so you could figure out where you were. Atmospheric refraction, displacement from the Earth's center. I'll deal with this eccentricity of the Earth's orbit and precession. Let's deal with these things now. Length of the year, you understand, because they're calibrating to the spring equinox. In 1582, you can see that there was a need to adjust the calendar. We went from October 4th to October 15th. Notice that what's the word for Friday? It's the sextile. It's okay. And of course, local noon. You understand that. But in studying the position of the sun, different points along the year, because they're mapping the orbit, Earth's orbit and position. They had Earth's atmospheric refraction, which was already understood, was studied to a much, much greater precision. Remember, when the sun, when we see it just above the horizon, geometrically, it ain't there. It already set. We're seeing the refraction. I believe it has been said that on Venus, that you would never have complete night. They would always have a little glow from the sunlight coming around. Now came the other thing. We get latitude, we get longitude, and then people decided they were going to map and triangulate the maps of Europe. Now, this started in Italy, because you had one Meridiana in one spot, one meridian in another spot. You know where they are relative to latitude. Now let's join them together with surveying, triangulation. And you get from one to the other, and they decided to do this across all of Europe. What you're looking at is the Cassini map of France. Now remember, Cassini became the director of the Paris Observatory. His son, his grandson, it was his grandson and his son, so Cassini III, Cassini IV. César Francois Cassini is Cassini III. Jean-Dominique Cassini was Cassini IV. I don't know if Cassini IV was director of the Paris Observatory, but that's not germane here. They mapped very, very carefully the map of France. One little problem. They found out that the west coast of France was about 150 miles further to the east than they expected. That's a problem because the King of France made his money on real estate taxes. He just got 100 miles less real estate. And they weren't too sure if they were going to lose their heads over this. Well, okay. I said 150. It was over 100 miles. But nevertheless, it was quite a controversy at the time. They found out something they weren't expecting. However, that was one of the things that was done. Another thing is offset from the Earth's center. Did you ever notice, like you read in the Sky and Telescope of Astronomy, a star is going to be occulted by an asteroid, and the shadow is going to pass in order to do that, you not only have to know very carefully where the star is and where the asteroid is, but where we are relative to the Earth's center. The way the math is done when you calculate motions is you're calculating as though the Earth or the sun is a point. That's how math works. And then afterwards you say, okay, now that we know that it's not a point, we expand it. So one of the earliest observations of Venus was nearly missed because the person thought that had done all the math. I thought that Venus is going to miss the sun. No, it's going to miss the center of the sun. If you look at the Observer's Handbook, it might say the moon will be passing in front of the Pleiades. It's going to be a quarter of a degree south of it. Well, is it going to occult the Pleiades, or is it going to be a quarter of a degree south? Well, the moon is half a degree in diameter. If it's a quarter degree south, it's going to hit most of the Pleiades. And that is what this was measured much more accurately. It was always understood. And like I said, when we see this now, and an asteroid's going to pass through a certain community, now people. Another thing is, again, this is exaggerated here, but the Earth's orbit around the sun, the perihelion, when it's at the closest, is in the winter. The aphelion is in the summer. So the Earth is traveling faster in the winter than in the summer. Spring and fall, the equinoxes are at opposite sides. What that means is since the Earth is traveling faster, these opposite sides are not opposite in the calendar, because winter half of the year is faster than the summer half of the year. The Earth is traveling at a different velocity. This was fought over. People said, no, if you're going apart at 180 degrees, no matter which way you're going, they're exactly half of a calendar apart. And this had to be measured very carefully. May sound a little... here's another one, parallax. Now, here we are looking at the Earth as being a point. Look at the moon. Now, when the moon is at its half phase, the angle at M is a right angle. So therefore, now remember, during an eclipse, there's a relationship between the size of the sun and the size of the moon. Because for all practical purposes, the moon is perfect. The moon is perfectly the same size visually as the sun. Now, sometimes it's an annular eclipse because the moon was further away. It was more aphelion. Sometimes it was closer, and it's at perihelion, and then we have a longer eclipse. But for rough purposes, they're the same. Good. If we find out that the moon is twice as far away as we thought it was, the sun gets 4 times further and 4 times larger, depending upon what our starting point. Good. Now with this, they measured the distance to the sun by measuring when M is a right angle. Gamma at the bottom would be not a right angle. And we determine a relative distance to the sun, not accurate, but relative. It turns out that gamma was nearly a perfect right angle. In other words, the sun is really, really, really far away, which means it's also really, really big. You don't mind if I'm using scientific terms here, right? Because they don't have an exact number, but they understood when, prior to all these measurements, it was, if you said that the sun was bigger than the Earth, that would not cause a major problem. Although people didn't know. In classical times, many times they thought that the Earth was huge and the sun rose in the east and was carried across the sky and set in the west. And so that would give us a small sun. This gave us a sun that was huge. That produced another problem because the Earth's orbit would be even more huge. Well, once we have a massive orbit of the Earth, take your telescope, which was invented by this point, point it to the stars, And why is there no stellar parallax? So long as we didn't know that the sun was all that big, the sphere of the stars would be, not so bad. The Earth's orbit would be relatively small. Parallax problem was not a huge problem. Now it was. That wasn't entirely proven, solved until the 19th century when telescopes improved to a point where they did measure some parallax. Okay. But now I'm just going to mention one last item. It's not really a Meridiana, but the Shrine of Remembrance in Melbourne. Remember, after World War I, there was a huge amount of grief in Australia. Australia lost a very large percentage of its young men. A lot of them fought in Gallipoli, which was a disaster. Never mind the losses on the Western Front for 4 years. But they had, and there was a need to, in 1934, this memorial was created, and it uses the principle of a Meridiana. Remember, the war ended November 11th at 11 a.m. 1918, the 11th hour of the 11th day of the 11th month. So therefore, on the 11th hour, 11th day of the 11th month in Melbourne, a shaft of light goes across and illuminates the word love. This is the quote from Gospel of John, chapter 15, verse 13. Okay, has nothing to do with science, but I wanted to throw it in anyway. Now, the book has only a couple minor issues with it that I saw. The very good book review that I saw in Sky and Telescope was very good. One, this is how the opening of the introduction goes. The Roman Catholic Church gave more financial and social support to the study of astronomy for over 6 centuries than any other and probably all other institutions. It's a wonderful statement. It is an eye-catching statement, which is what you want on an introduction. And I think I pointed out that it's not entirely correct. Several of these churches were secular. They were used by the Catholic Church, but they were owned. The one in Florence, the one in Bologna, and the one in Rome, certainly. I don't know about the one in Florence. But those two were secular owned, and it was the city councils that built and financed the Meridiana. Keep in mind, at this time, churches were multi-function buildings. Today we have they don't have sports arenas then for churches, but convention centers, trade halls as well. These were all done in churches. Having a large church helped bring business in. If you want a good study, the story of the cathedral in Chartres in France, they'll give you a whole story about that, because it was a center of trade at that time till other roads were built. So I don't think this statement is correct. What I have found, and this is my criticism in terms of scholarship, is, and I've done this in other areas. So if you have a religious person, they don't understand the astronomy and the science. They understand the theology. You get a scientist, they can study these instruments and give wonderful texts like this book about the science, but they don't understand the theology behind it or the history of the church. That's the one weakness. If you take that away, this book goes into a lot of detail. It's how many pages, by the way? I didn't bother to write that down. It's over 300 pages. A lot of it goes into how the calculations were made, why they were made, etc. It is a bit heavy for somebody who's new to astronomy. So a good book report tells you what the good points are, the bad points, and who the audience would be. And I would say it would be somebody who's well-educated, who wants to see something a little deep. But if you just want to see the pretty pictures, that's great also. I'm going to stop sharing and open this up for discussion.